Hi everyone. Today is lecture 13. So this will be the last lecture that's covering the fundamentals of the course to some extent. And starting from next lecture, it will be students who are giving the presentation. So they'll cover the background as well as the paper that they are interested. You get a sense of the topic. So today we'll be talking about object detectors. So before we go into the technical details, some administrative stuff. So project 3 is released. We still are working on AutoGrader. It will be up soon. You'll see an announcement from me once the AutoGrader is up. But that shouldn't stop you from getting started on the project. So do get started. Although next week is a spring break, it's due on 14th, the week after, like as soon as you come back from the spring break. So do spend some time in doing this. Okay, coming back to the final project tasks. So paper selection is done. Thanks to everyone for deciding what paper you wanted to work on. I saw that on the spreadsheet, so I think we are good there. If you are making any modifications, do let me know. Final project proposal is due on 2nd, which is on Thursday. I sent out a LaTeX template, but you can create a Google Doc or document template, but it has to like look closer to the LaTeX template. The idea here is, again, you'll email them to me on Thursday. I'm making it soft deadline. So Thursday would be great, but if you're doing it on Friday, it's totally fine. The sooner you give me, the sooner I can give you the feedback. The idea is I can give feedback to each of the proposal with my comments. So you can incorporate that, think about it as a team, and come back on 14th to do the the project pitch. So this will be on 14th once you come back. So this will be a short video that you will create with your team. And it's easy, just go on Zoom, create your slides and just talk over the slides. But think about pitching it to the other teams in the class. So you want to talk about your project, what is the goal, objective, who are you guys, what each person is working on, what is the re-implementation here or reproduction here is going to be about, and how are you distributing the work among you three. And if there is a plan A, plan B, then you want to talk about that as well. So this should be very short. Think of it like an elevator pitch where you're trying to convince other people, you're getting them excited about your project. So, and we'll try to have like a in-class rating with other teams. So I think it'll be fun to get a feedback on various aspects. So we'll do that as part of the class on 14th. So the in-class topic presentation is going to start from next lecture. I know the first group is already working on that. And like I said, if you're presenting it, you probably want to like talk to me in my office hours the previous week. Yeah. Okay. So in the last lecture, we saw what is transfer learning. So we talked about two different ways of doing it. One is extracting the features, followed by training the last layer, or changing the weights of the last layer by freezing all of the backbone. The other way to do that would be what we call fine-tuning, where you will use many more blocks starting from the final layer to train your network for a new data set or something like that. We also talked about localization task or object detection, how classification is being used as a building block for doing object detection. And more specifically, we talked about RCNN, which is region-based CNN. So two outputs that comes out of RCNN is one is the classification of a detection, and the other one is a bounding box regression, which in this case is a transform with respect to the region of interest that was given to the convolution network. So if you think about it, on the left side, to give a recap, we have an input image, and there's a black box region proposal. We'll talk about that towards the end. But if you want to think about it, it's like some heuristic-based region proposal that gives you a bunch of regions from your input image. And those regions are warped such that they are of the same size. In this particular case, 224 cross 224. Goes through a convolutional neural network or a backbone like AlexNet or VGG, whatever it is. And then predicts the class and also regresses the bounding box in terms of the transformation. So that's the idea behind the region-based CNN. So in fact, this was one of the first neural network-based detectors that came out that could be used in a setting. So the problem here is, if you have already noticed, the region proposal module, whichever it is, it's a black box. In this particular case, it was proposing around 2,000 proposals. So imagine per image, you have 2,000 regions that are being proposed. So you are running through the AlexNet like 2,000 times to get the detection and the bounding box. So if you remember, we talked about non-maxima suppression, which kind of eliminates the overlapping bounding boxes, which happens after that. So we are having this computational bottleneck of evaluating each of these region proposals using your convolutional neural network. So the one way to kind of account for that is you understand that these regions can be overlapping, which means you are computing the features again and again and again. There's a lot of redundancy that's going on. So the next work, which is fast RCNN, which has authors from RCNN2. So they propose something where you will extract features using one, let's say, a backbone convolutional neural network, which gives you image features. And then you will start getting the regions that are on the image features. So you are kind of reducing the process of repeating the feature extraction that you see in this particular, what we call slow RCNN. And after that, each of these image features have to be resized, cropped and resized, and goes through CNNs, which are similar to what you saw in slow RCNN, but here it's like per region, and regresses the bounding box as well as does the classification. So that's the basic difference between the RCNN and the fast RCNN. Is that clear? The difference? So instead of having the proposals done earlier, you're doing it after the feature extraction. So if you think about it, there are two big blocks. One is used for feature extraction, which you can call as backbone. And the other one is per region network that does the classification and regression. If you think about the image classification networks that we saw earlier, the backbone could be the backbone that you have from the AlexNet. And the top layers, where you have fully connected layers doing the job of classification, could be your per region network. Yeah, so connections between image classification networks. And for instance, here you can see ResNet. So there is a ResNet block, at least the backbone, and then you can use the stage that is after the initial set of blocks for your per region network. So now I think you should still be like wondering, like, how do we do this cropping and region extraction in the feature space, right? So how do we do crop in the feature space? So to do that, we will go back to the concept that we saw earlier, which is receptive fields. So in this particular example, you have the input image, which is of 8 cross 8 dimension. And it goes through a convolution layer, which is 3 cross 3 with stride 1 and padding 1. you get an output image of 8 cross 8, right? So every location or every cell in your output feature map has a receptive field in the input. And if you change the convolution operation here, let's say you have two convolution operations, like 3 cross 3 followed by another 3 cross 3. So your receptive field is changing, but you can imagine that there is a correlation between every cell in your output map has an input region that is corresponding to. One other way to look at it is like if you move the cell to a different location, correspondingly there is a change in your input as well, right? The receptive field in the input space. So with that, you can actually build not only a discretized correspondence, you can also think about having a continuous correspondence. For instance, if you think of input and output to be not in terms of discretized cell structure, let's say it's from 0 to 1 on both the axes, you can think about a continuous way of finding a correspondence between a location in the output map to what you have in the input map. So to make it clear, let's say you are looking at not a particular cell, but some random location in the space. It will have a corresponding location in the input. And this will also work if you are doing, let's say, if the output feature map or output map is not of the same size as your input. For instance, let's say you have the output to be 4 cross 4, you will still have the correspondence, although you are discretized because of your operations, but you'll still have the correspondence if you want to map back. Same thing if you are doing, let's say, much more downsampling here. So this is the idea behind figuring out the cropping and region extraction in the feature space, while you know the proposals in the input image space. So for instance, if you have a region proposal, so let's say you have a black box that gives you a proposal in the image space, you don't have to use it right away, but you can find the same region in the feature space. That's what we want to do it with fast RCNN, right? So so let's look at a more concrete example. So you have an input image, which is 3 channels, 640 cross 480. It went through a convolutional neural network and giving you a feature map, which is 512. So each feature is 512 dimension, and you have 20 cross 15 as your the dimension of your feature map. So let's say at the end of this, you want to give it to a per region network, which will take input of 2 cross 2. So if you remember the block, we had image followed by feature extraction, and then you do the cropping and resizing, followed by the region network, right? So just assume for this particular example that your region network always takes input of 2 cross 2. In practice, it will be like 7 cross 7 or 14 cross 14, but for this case, assume it's 2 cross 2. So this is how you will find a correspondence in the feature map. So again, if you see, it's not exactly fitting into the grid structure, but that is the exact proposal that you got on your image space using a region proposal module. Now, one simple way of doing this would be to snap it to the grid cells, figuring out whichever is the closest corner for these proposals. You snap that to the grid cells, and you'll figure out like what are the sub regions, because at the end you want 2 cross 2. So you are again trying to fit it to the discretized structure of your feature map, and then you can perform some sort of max pooling to get it back to the 2 cross 2 that your region network is expecting as an input. Yeah. But the problem here is that the snapping to the grid cells looks a little weird, right? You might lose some information. Your bounding box might not be perfect. So which will result in some inconsistency if there is a shift in the image space a little bit. So the other way of doing this is what we call ROI alignment. So this is a little bit involved. Instead of doing the snapping, to the grid structure, you would want to retain the structure that was coming from the proposal. So the green bounding box that you have with 2x2 regions is from your proposal, and you want to use it as such and not change it for the grid structure of your feature map. So one way to do that would be to kind of figure out the regions inside of the original region proposal bounding box, create the subregions, and extract features by using this concept of bilinear interpolation. So let us take some examples to understand what that is. If you take a closer look for this particular region for which you want to come up with a feature, if you look at the closer grid structure, which looks like this, you can use this information to extract feature at this location. You already have a feature in these locations because you are looking at the feature map, but you want a feature for this particular location. So using the math that is described, which is basically a weighted averaging over all of the features, you will compute, let's say, with respect to this particular feature, which is at a distance of, let's say, 0.8 and 0.5, you can come up with a weight that corresponds to that particular feature. So you can do this for every feature. For instance, you do this for this one, and the other F66 and F76. So the idea is the closer you are to a particular feature map, the closer you are to a particular cell in your feature map, the more that feature will actually play a role in your final feature. Is that clear? As opposed to snapping to the grid? Questions? Okay. So now you can go back and do your max pooling in each of these regions once you constructed these features. And then that you can use that for your region networks to give you the class label and also the bounding box regression. Yeah. So we talked, yes.
So the region which you select for max pooling, is it like arbitrary and fixed, or does that change based on the feature? Like in the example you showed before, there were like unequal, like in the very beginning after the snapping part, there were unequal rectangles.
Yeah.
But then now they're equal.
Oh, you mean, oh yeah. So this was, the whole point here was the snapping and adjusting to the existing grid structure. So you have to figure out like these 4 regions in one way or the other. So the easiest way to do that is like, okay, take 2 rows for the top 2 subregions and take 3 rows for this one. So it was like a decision based on figuring out how closely you can be to your grid structure. So the other way to do, this is probably a design choice. You can also do the other way. You can have 3 followed by 2.
So it's something which is fixed throughout. Like you do that.
Yeah, you make the design choice for the entire.
Yes. And so if we go back to the bilinear example, where they like the first one where you take the distance to your F65. So that's the 0.5. Yeah, that one. Okay, I see.
So there is 1 minus of the L1 distance. Yeah. Yes.
So like the region proposal mechanism is still giving us the regions. We're just mapping it onto the feature space and then putting all the features together at once to
Yes.
linear network.
Yeah. So the region proposal module, whichever it is, takes the input image and gives you proposals. That's how it is. But when are you going to use that proposals is what is the difference between the slow RCNN and the fast RCNN. In the slow RCNN, you use it just after the image, take those regions, warp the image, and send it through the convolutional network. Whereas in the fast RCNN, you're like, we're not going to do it right now. We're going to do feature extraction for the entire image, and then do the corresponding regions, crop the corresponding regions in the feature map. So that's what we are looking at right now. Yeah. Yes.
So does this happen before, or
This happens before max pooling operation?
You mean non-maximus operation?
Or, so I see we have 4 of these points per region, so with these regions, would we then be max pooling?
Yeah, so you will get features for all of these green dots using this map. So which means you'll have all the values right now, and then you can do a max pooling on these 4, which would give you one particular feature. Yeah. Okay. Okay, so to give again an outline between the differences of fast RCN and slow RCN, it's just that the application of the proposals happen after the feature extraction. That's the main difference. And to look at the gain in terms of computation, so if you look at the training time, RCNN was taking about 84 hours, whereas fast RCN takes around 8 hours. So there is a huge difference in terms of computation. And in testing time, fast RCN is like 2.3 seconds. Sorry, 2.3 plus 0.32. So it's actually talking about 2 things, including the region proposal and excluding the region proposal. So I think excluding region proposal is faster. So we haven't talked about the region proposal yet. So I want to make that clear. So we are assuming some black box is giving you regions, right? It's based off some heuristics. You can do image processing that gives you like, oh, these are some of the blobs that I see in the image. So let's draw a bounding box and say that's a particular proposal. So that step is what is taking larger time in your inference during inference. Yeah. So the next version of RCNN, which is faster RCNN, is trying to reduce that bottleneck in terms of proposing regions. So the algorithm that is proposed is more of a learned network. So instead of having something called selective search, which is what RCNN and fast RCNN uses, the faster RCNN comes up with a learned network that gives you proposals, which is faster than the selective search approach. Okay, so basically the faster RCNN has this region proposal network, which takes in your feature map and gives a bunch of proposals. Not the feature map, the input image, and gives you a bunch of proposals. So let's take an example to see how that looks like. So you use the input image, run that through a backbone, which gives you image features. And just to note, the image feature here is 512 cross 5 cross 6. So the feature map is downsampled much compared to your input image, right? Now the region proposal network has to figure out like what are the regions in this particular image. So the way to do that is to figure out these points correspondingly in the input image. So you have this 5 cross 6, that is your grid structure of your feature map. So assuming each cell to be a point, let's say it has a corresponding point in your image space. Now you can come up with an anchor region. This is different from your receptive field. So anchor region is something you fix. You say, okay, this is the size of this particular anchor region, which will have a center point that corresponds to a cell in your feature map. Okay, so I'll repeat this again. So you have 5 cross 6 as your grid structure. For each grid, there is a corresponding region in the input image. And you have decided an anchor box of fixed size that you are thinking will be the bounding box or the proposal that is corresponding to this particular grid. Now, a simple thing that you can do is by saying, okay, can I, so for instance, this changes for every grid. I think that is pretty clear. The simple thing that you can do is to say, classify each of the grid to say whether it has a proposal or not. So all of these 5 cross 6 cells, let's say that they go through a classifier, and you can say, is that an object or no? That's one way to do the proposals, right? So for instance, here, you are selecting this particular grid in the feature map and classifying that as, okay, there is no object in that region or in that particular anchor box. So it's not an object. There is no proposal there. For instance, if the feature here is an anchor box of that size, you can say that, okay, that probably covers a cat, so it's an object. See the difference? So you're trying to classify each of the cell in your feature map to say whether there is an object or not. Yes.
Does this anchor was the size of the receptive field?
No, not necessarily. So it's something that you can fix, and you'll see in few slides that you can have many anchor boxes for a particular feature.
And like, how does that work? I can choose an anchor box bigger than the receptive field.
Yeah, so the idea is because you downsampled so much during the feature extraction, you have a good coverage that basically says you can figure out an anchor box based off of maybe the downsampling that you have to say that these are fixed number of anchor boxes for every cell in the feature map that I can classify whether it has a object or not. So you'll see like some examples that might clear that up. Okay, now you have, let's say you take another example and your classification says that's not an object. In terms of the structure, what you will do is you will pass this image features into the region, something similar to the region network, or in general, a convolutional network, to get a map, output map that is 2 × 5 × 6. So 5 × 6 is the size of the feature space here. The 2 is basically saying yes or no. So you have two scores for whether there is an object or not. You can also add transformation so that the network also outputs 4 × 5 × 6, where 4 is X, Y, W, and H, which gives you a bounding box that kind of changes the anchor into the ground truth bounding box that you have. So this will be done only for positive samples. Like if there is a, if the anchor says that, if the output says there is a object, then you will have an anchor transformation for that. So you can have a gradients from that. So like I was saying earlier, it need not be one fixed anchor box. You can have many anchor boxes of different sizes, different aspect ratios. So for instance, you can decide what a K is. That says for every feature map grid, I'm going to say it is corresponding to a bunch of varying regions or anchor boxes. And together, I'm going to classify whether that region is has an object or not, whether it's a valid proposal or not. So you can have many outputs. So earlier it was 2 × 5 × 6. Now you can have 2K × 5 × 6, which means for every channel, you have a score that says it's whether it is an object or not. Does it make sense? And for every proposal, you can have a transformation that gives you the change that you have to do to make it closer to the ground truth bounding box. Yeah, so we are still talking about region proposal network, not the object classification or bounding box regression. This is just like trying to propose a bunch of proposals for you. Yes.
Wouldn't the size of the anchor box be limited by the downsampling that's done when we are creating the feature?
Yes.
So
that's what the earlier question was. So he was talking about whether the receptive field will affect the anchor box. Yeah, so they will have some correlation.
Would that be like upper limit? If I, let's say, do something in this region, the anchor box can't be larger than that?
I think so, but I don't know if the paper has any ablation study on that. But yeah, but that's a good question. Like maybe you can check into that. Okay. Okay, I think we saw that. Yeah, the positive anchors are basically if there is a 0.7 IOU with your grounding ground truth boxes. Same thing with the negative, and you'll have neutral anchors as well that you can ignore during the training. So you can actually sort out these proposals at the end and only pick a fixed number of proposals that will go up for your classification and regression. So earlier it was like 2,000 per image. Now it will be probably in hundreds to do your, sorry, not 2,000. 2,000 was for RCNN. Yeah, so we are comparing with RCNN, then yeah, you'll have in hundreds. But we have a proposal network instead of having a heuristic model for fast RCNN. So we talked about RCNN, fast RCNN. And faster RCNN is where you have a neural network for region proposal, whereas the other two had like some sort of selective search based method for doing the proposals. Okay. So in terms of losses, you'll have 4 different laws. One is for the region proposal classification, whether there is an object or not. The other one is region proposal networks regression, which gives you a transformation with respect to the ground truth bounding box. And then there is object classification and object bounding box regression. So there are 4 different losses, and you'll use all of them for training. Yeah. Okay. So in terms of computation speed, yeah, fast RCNN is much more faster because you are not having an algorithm go through your image and do the processing to give out proposals. It's a neural network, which is much faster to give you that proposals. Okay, so to kind of extend this idea, there is another work that came out of the same set of authors, which is called mask RCNN. So this has something called instant segmentation, where there is a little bit of an extension. So you have a bounding box that talks about a particular object. You might as well like figure out the class of each pixels in that bounding box to give a segmentation. That's the idea. And specifically, this is instant segmentation because you're talking about a particular instant of an object. So if there are people, you'll be like person 1, person 2, person 3. Each of them will have a different bounding box, and they will have their own segmentation. Okay, so yeah, the approach, as I said, it's like you do detection followed by segmentation for each detected object. So it's very simple. You just add one other readout network that uses your regions to do the segmentation. And to be more specific, you have convolution layers that are operating on your regions that were proposed to give you a classification over all the classes that you have. One thing to remember is, although we have, let's say, C cross 28 cross 28 here, your ground truth will only be with respect to one particular object. The rest of them will not have any value. So you'll only use that information to the back propagation. Yeah. So the output of mask RCNN basically looks like this. So you can see that there is a segmentation which has a corresponding detection with a label. So it cannot have a different label as opposed to what the segment particularly has. So it has to be corresponding to that. So that's something to make sure you know. Yeah, so mask RCNN is very popular, and it's one of the go-to networks for testing if you have segmentation as your application. And it works really well. But again, you can do fine-tuning on top of it to make it robust for your task. So one example of like how people extended mask RCNN would be to add another predictor, which is key point detection in this case. So if you have a person in the scene, let's say human anatomy is like having like certain key points that describes a person. So you can try to regress the key points using the same network. So yeah, so the key points could be like left ankle, right ankle, and so forth. So it's basically a key detection of a particular feature map in your regions. So this looks like this. So basically, it was purely for people detection, followed by the key point detection on top of it. So you can see we talked about classification, bounding box regression, then came in segmentation, and now specific to people segmentation and detection, there is also key point detection that you can do. So which gives you a little bit closer to pose estimation of people in the scene. Okay. So we talked about RCNN, which is basically a two-stage object detector. There are single-stage detectors as well. So one example would be your YOLO. So we'll not go into that in the lecture, but we'll give you references so you can look into that. So when I say two-stage, basically the first stage is you have a backbone network, and which is followed by your region proposal network. And the second stage is where you'll use that information to do classification, regression for your bounding box. And if you're doing segmentation, then segmentation and so forth. I think with that, we are to the end of lecture. So next time you will see a student presentation. I will also play a role in that because they have only 2 people in their team. It will be RGBD perception and network architectures in that space. So yeah, I'm ending the lecture way early. If you have any questions, I'm here. I'm here till 3:40. Happy to answer questions.